All right, welcome back to the hardware track here. We're going to move just ever so slightly further up the stack to the trusted boot UEFI. For those of you who are not familiar with this technology, this is us trying to tie further into the hardware to make it harder for attackers to come in and compromise customers. What we have today with Jean-Ian and Frédéric is talking about a nation-state actor. Those of you looking for Russian intrigue, this is the talk to be at today. STRONTIUM is one of the Russian players that we track here at Microsoft, amongst another couple of names, including Fancy Bear there. Today, they're going to walk you through their research on attacks by STRONTIUM into the UEFI space. So with that, please welcome them to the BlueHat stage.
All right, thank you, Philip. Welcome, everyone. Thank you for being here. So, as you can tell by our title, we're going to talk about UEFI Rootkit. So, as Philip said, STRONTIUM is a ATP group that is known with various different names. So at ESET, we call them Sednit, and this is a name I'll be using because otherwise I'll get all confused up on stage, and this is not something I want to do, but STRONTIUM is the Microsoft name. It's also known as APT28, as well as Fancy Bear, Sofacy, and is believed to be behind a lot of notorious hacks that happened in the past few years. I'm sure most of you are aware of the hack that happened last election, for the US election, the DNC hack. So they are believed to be behind that. Also the WADA hack, so the World Anti-Doping Agency, they saw their email being leaked by a group. We believe that they are behind this hack as well. And we know that this group has been very active, targeting all types of organizations around the world to gather more information and spy on them, basically. And we know that they've been using different tools, so backdoors, first stage backdoor, second stage backdoor, but we never knew them to be able to develop and use UEFI Rootkit. And this is what we are going to present to you today. So the analysis of this UEFI Rootkit, as well as a bit of our hunting game that was behind all of this. So being able to uncover these type of things takes some time, and we're going to walk you through each step that led us to this discovery. So briefly, I'm Jean-Ian Boutin. I'm a malware researcher working for ESET based in Montreal. This is my colleague, Frédéric, and we basically did this research together. So in a nutshell, what we're going to see today is first we're going to go a bit on what is LoJack. So I guess that many people here are aware of this anti-theft software, and why we're talking about this is because this Sednit group, they actually use a trojanized version of the userland small agent of LoJack to be able to connect to a communication control server and have the capability to download and execute code. So we're going to first take a brief look of this solution and look at the past research that happened on the older version of this agent. So several researchers were published about this anti-theft software, and they basically put in evidence some of the vulnerabilities that were affecting this software. Then we will tell you how we dug into our telemetry and eventually found a UEFI rootkit. So let's start. So as I said, LoJack was what was known as CompuTrace in the past, is an anti-theft software. So it is built by this company, Absolute Software, and it's basically meant to allow people that lose or have their laptop stolen be able to recover it. And of course, when you have this type of anti-theft software, you need it to be as persistent as possible. So one thing that made this software very interesting for research purposes is that it had this BIOS module and UEFI module that allowed them to survive security measures such as reinstalling the operating system or replacing, let's say, a hard disk, right? Because this module was able at boot up time to replace the agent that was placed on the computer and be able to recover the laptop should it be stolen. And just in a nutshell, the capability of this agent, it's able to reach out to a server, and then it can locate it through various means, such as GPS tracking or Wi-Fi triangulation. And it can also lock it remotely, so it can receive commands from the server to lock the device so that people that are in possession of it are not able to access it. You can also remotely delete or wipe the entire system, meaning that a hardware loss will not translate to a data leak. So this is something that might be appealing to corporations. And then you can also use that to try to recover your stolen laptop. So this is really briefly what this anti-theft software does. So let's look at the past research. So as I said, there is this UEFI module, BIOS module, that is in this software, and it attracted a lot of attention from security researchers. The first research that was publicly released about, and that was being able to detail a lot of the vulnerabilities, is this one. So it was published in 2009, presented at BlueHat USA, and it was basically detailing a lot of vulnerabilities that are present in, that was present at that time on the small agent, computerized small agent. And now I just want to iterate that all the vulnerabilities we'll see today are affecting only past versions of the agent. So this is not the solution that exists now. It's really past agents that suffered from these vulnerabilities. So this is a infographics that shows a bit of the architecture of the anti-theft software as it was known in the early 2000s. So the first step is this BIOS module. So what it would do, it would contain the agent and was able to dump it to the disk. And how it would do this? It will actually replace the autochk.exe. Many of you might know what this does. It's early startup of Windows. It will check your hard drive for its integrity. And of course, by replacing this file, once Windows starts, it will be able to execute. And the responsibility of this one was to register the small agent as a service and make sure that it would be launched every time that the system would start. The small agent itself, its main purpose is to make sure that the full recovery agent, so the agent responsible to communicate with the CNC server, is always present on the system. And if it's not, it's able to download and execute a version from Absolute Software Server. And how it does this is interesting, because it will first spawn a service host process, injects it, and change itself as a DLL, inject into this process, then spawn an Internet Explorer process, and then inject this DLL again. And from this Internet Explorer process, will then reach out to a server to try to download and execute stuff. So this is not something we see that often in legitimate software. This is behavior that is very, that we see all the time in malware. So this is a bit different. We don't see this a lot in legitimate. And then the last step is, of course, the full recovery agent is running on the system, and it's able to receive command from the CNC. So I'm going to show you only one vulnerability that was found at that time, because it's the only one that really matters. So here you see a part of a small agent from LoJack. So this is its configuration file. So it's one way that they use to get the server where it will connect. And as you see, not much can be seen from there. It's actually encrypted, but it's not very using tough encryption. It's actually XORed with a single byte XOR key, which is B5 in that case. And as you can see here, you can, in clear text, you can see the domain that it will try to reach out to should to download the full agent. So, of course, this is not very secure. There were no authentication done at that time. So if an attacker had access to the to override this configuration file, it could change it and change the server that the small agent will connect to. So as I said, the URL is visible once decrypted, and the 4 bytes preceding it is actually an IP address. So the small agent would use this information to know where to connect. So this is one vulnerability that was highlighted. If we fast forward to 2014, there was another very interesting research made by, published and presented at BlueHat, and that was partly made by Kaspersky, and they basically documented the whole network protocol that was used by the small agent, making it even easier for an attacker to actually be able to take control of the system, basically. And how this solution works is that the Absolute Software deals with a lot of OEM manufacturers, so firmware manufacturers, so that their BIOS module is included in a lot of laptops. So if you looked up in your BIOS settings, there's a good chance that computerized will already be installed on your system, and all you need to do is activate it. And what Kaspersky discovered is that in some cases, there was some silent activation of the thing, so another thing is of concern. So if we do a little recap, what I showed you is this configuration file, which is kind of key in this whole Lojax campaign, because it's quite easy for this old agent to change this configuration file and then control where the small agent will connect to. So that's kind of the end of the small introduction. So now it's time to dig in. So at that point, like, we didn't see wide campaign using these type of vulnerabilities to try to compromise systems. That was until last May, where a blog from Arbor Networks was published. Basically, what they found is that a lot of trojanized small agents were in the wild, and they see that the agent is the same as the legitimate one, but only the configuration file was patched with new domain and new IPs. And they were able to link these new domains to all domains that were used by the Sednit group in the past. So this is how they were able to see, okay, there's most likely a link between this LoJack campaign and Sednit. So this is really the starting point for us. So we saw this, we said, okay, let's look in our telemetry to see if there's something more. Because if we go back to the architecture I showed you, so the old architecture from 2008, if we see only the LoJack sample small agent on the system, the most likely way that the agent is on the system is just by dropping it. And we know that Sednit has several backdoors that give them full control over the system, meaning that they could just use a small agent to, as another persistent method if they should lose access to network, a way to regain it, right? And the fact that this software is legitimate, it's whitelisted by a lot of AVs, so it makes it easier to go under the radar. So just that is actually a good thing. But we still wanted to see if they try to mimic the full LoJack solution a bit more. So this is one of the configuration files that was altered by the attacker. And what's interesting is that they all use the same sample of the legitimate LoJack small agent. So it has all the same compilation timestamp from 2008. And all they did is to overwrite the couple of bytes from the configuration file, changing the IP address, changing the domain name, as well as some other stuff. But mainly, the bulk of the small agent is exactly the same. But since they were using all the same thing, it's actually easier for us to see and track all of these samples that occur in our telemetry. So this is what we did, and we found a few organizations that were hit by this LoJax campaign. And it's interesting to note here that Sednit is targeting a lot of organizations around the world, and this LoJax campaign targeted only a few of them. So this is not as widespread as the other campaign we see. So the verticals were mostly military and diplomatic organizations, which is in line with the traditional targeting of Sednit. And in the systems that were that LoJax was found in, we also found traces of other Sednit tools. So a typical infection from this LoJax campaign would be X-Agent. So for those of you not familiar with Sednit, X-Agent is kind of their flagship backdoor. This is what we found on a lot of systems. They use it to execute code to spy on the victim, basically. It's a regular backdoor. Then you have External. External is a proxy tool, so it allows them to reach computers that are not directly connected to the internet. So they use this External on a computer that has access to the internet, and they can relay the command to computers which do not have connection. And then finally, we saw Lojax somewhere in between these. And we didn't know at that time how the small agent was appearing there. So, of course, as I said earlier, the most likely explanation would be that the X agent would be used to drop the small agent, but we still wanted to dig a bit more, right? I just want to highlight some of the stuff about these LoJax infection. So in some cases, we saw LoJax that was like the only thing that was on the system was LoJax, which is interesting by itself because, as I said earlier, these software, since it's a trojanized version of a legitimate software, it's likely to be whitelisted. So if you have only this on the computer, it might help you to regain access should you lose access to the network. They were also updating the configuration file of these LoJax agents, so they were able to update the sample there to make sure that their servers were always available. And then finally, for the small agent stuff, how we link it to Sednit, well, Arbor already stated that the domains were reused from past Sednit campaigns, and we saw the same thing. So IPs and domains that were used in previous campaigns were also reused in Lojack's campaign. Then the tooling, of course, these compromised organizations also had other traces of other Sednit tools, and then the targets were kind of the same. So if we put all that together, we can assess with high confidence that this is linked as well to Sednit. So now let's go a bit wider. So we've assessed that this Lojax campaign is consisting, of course, of the small agent, but let's try and see if we cannot find something else. If it's not only userland, but going a bit deeper, right? And last week, there was an interesting blog that was published in the Virus Bulletin blog. Virus Bulletin is a security conference. It's going to be held next week in Montreal, in fact. And there was a guest blog from Kostin Ryu. I guess many of you know Kostin. He's the director of Great at Kaspersky. And he basically wrote an article saying where are all the A's in the APT. And what he meant by that is that, well, a lot of cool security research is happening all the time, and we don't see these groups reusing the really high-hand result of this research. And he then listed a couple of things he said we might see at some point, and one point was this one, which was we have yet to observe real-world UEFI malware. So let's see if we can cross that one out. Before going deeper, I just want to show you this. So this is the GUI of a tool called RWEverything. So it's freely available on the web at readwriteeverything.com. And basically, it allows you to read and write different configuration items at very low level, at the hardware level. So it allows the user to see a lot of configuration items. And to do that, it uses a driver. So the driver is a kernel driver, of course. It's signed. As this is legitimate software, it is signed, of course. All kernel driver now in Windows need to be signed. And this driver, we saw it used in different tools to be able to access this low-level information. And we actually found it in one tool that was alongside some Lojack's compromise. This is a tool called UEFI.exe, and all it does is to dump a lot of information on the low-level settings of a platform. Here I'm showing you a snippet of the log file that it produces when it's executed, but of course it is much longer than what I'm showing here. And of course, if you want to go and develop a UEFI rootkit, this is the type of information you need because it's really hardware dependent, so having access to the platform settings is key to be able to develop a UEFI rootkit, right? So this is kind of the first sign that led us to believe, okay, maybe there's more to this story. Maybe it's not only the small agent, but they actually went a bit further. So if we go back to the original architecture I showed you before, the step before the userland is actually the autochk.exe, the one I discussed previously. And interestingly, we did find something that looked quite a bit like this. So it's a file called autoche.exe instead of autochk.exe, and it does something very similar to what the real autochk.exe from Computrace is doing. First, it will register a service with this name. This is the original name, the legitimate name that the Computrace agent would use. It will then register the RPCnet P, so the small agent executable, as the service, so it will be ran each time the service would start. And then the interesting part is that you cannot see very well here, but this is basically a string that is autochk.exe, and it's actually writing it to the boot execute registry key, which is the key that holds the path to the autochk.exe, meaning that it puts it back to the original value. So at that point, we didn't know exactly how this autoche.exe was launched, but we knew that they were overriding the registry key to its original value. So let's try to find something else, right? So the first tool that really put us on the right path is this one. So it's called rewriter_read.exe. It was found in some Lojax installed as well. And how its only purpose is to dump the SPI Flash Memory. And how it does that is by using this read-write-everything driver, and in the table here you see the different input-output control code that it's using, so it's able to read and write from memory mapped I/O space, also read and write in the PCI configuration register. So these are the IOCTL that this tool uses from read-write-everything. And the binary itself contains a lot of debug strings, so this is very cool for a reverse engineer because it's that much easier to actually know what is going on, but also it indicates that the tool was most likely being developed heavily. So it had 3 main operations. The first one was to log information on the BIOS control register. Frédéric will explain why it needed this. The second thing was to locate the BIOS region and then read the UEFI firmware content and dump it to a file. So how it would do this? Quite simple. This is a very standard procedure to read the UEFI. So what it will do is that it will first put in the hardware sequencing flash control register the address, the number of bytes that it wants to read, so in the field flash the byte count. And then it would go ahead and set the read operation into the flash cycle, so 00. So meaning that the flash chip knows that it will need to do a read operation. Then what it will do is that it will write the address it wants to read into the hardware sequencing flash control register, then write one to flash cycle go saying to the flash chip, let's go read the operation. It will then wait for the whole read cycle to finish by looking at the specific field, the SPI cycle in progress, which is a field in the hardware sequencing flash status register. And as soon as it's 0, that means that the read operation is done and that data is actually available in the flash data register. So the program will read it from there and then put it in the file and dump the whole firmware image using this whole procedure. So now we'll let Frédéric walk you through the rest of the presentation.
Okay, so the next tool that we found on some system is called RWEvrything binary. And this tool contains a lot of debug strings that is very similar to RWEvrything read. And it also uses read-write-everything's driver. So now that the UEFI firmware is dumped, the next thing that this tool will do is that it will add the UEFI rootkit to the firmware in memory, and then it will write it back to the SPI Flash Memory. So let's talk about the patching the UEFI firmware. So before we dig into this, I just want to introduce a couple things here, so just to make sure that we're on the same page. So let's first define what UEFI is. So UEFI stands for Unified Extensible Firmware Interface, and it is kind of a replacement for the legacy BIOS. It is kind of the new standard for firmware development, at least for the PC platforms and for the laptops. And UEFI is a specification which standardizes the interface that exists between the firmware and the operating system. A UEFI compliant system will provide a set of services to UEFI applications, and here just read operating system loader. There could be some other UEFI applications, but usually it is an operating system loader. So the services that will be available are the boot services. These services will be available until the operating system loader is executed, or more precisely until it calls exit boot services. And there are the runtime services, which are the services that are available even when the operating system is running. So what's interesting with UEFI is that there's no more master boot record or volume boot record involved. So there's no easy way to hijack boot control flow just by writing to the first sector of the disk, for instance. The second thing I want to introduce here is, well, are the driver execution environment drivers. So they are called the DXE drivers. So they are PE-cuff images, so basically Windows executables. And they can do many things. They can abstract hardware. They can, some of them will produce the UEFI standard interface, so the boot services and the runtime services. And they can also be used to extend the platform by registering new services, the so-called protocols. So the DXE drivers are loaded during the DXE phase of the platform initialization, which is a phase that happens before the operating system loader is executed. And the DXE drivers are loaded by the DXE dispatcher. We'll also refer to this as the DXE Core later on in this presentation. Now, the last thing I want to introduce for now is the UEFI firmware layout. So the UEFI firmware is located in the BIOS region of the SPI Flash Memory. And this region will contain multiple volumes. These volumes will contain files. Let's just look at it in UEFI tool, which is an open source project for manipulating UEFI firmware. So here we see the typical content of a SPI Flash Memory dump. The first thing that that is there, hopefully you can see this, is the descriptor region, which gives some metadata about how the data is laid out in the SPI Flash Memory. Then we have the ME region, which is the Intel Management Engine region that contains the Intel Management Engine firmware. And we have the BIOS region, which is the part that interested us now. So the BIOS region, as I mentioned, contains multiple volumes. So let's look at how it looks. So here we have a volume. This volume is an FFS v2, meaning a firmware file system version 2, and it contains multiple files. These files are named by GUIDs, that's what we can see under the name column. And when we expand the file, we have multiple sections. One of these sections is the actual UEFI image, that's what we can see, the P32 image section. But there are other sections like the DXE dependency section, which allows to define some dependencies for UEFI executables. There's the version section, which is pretty self-explanatory. And there's the user interface section, which allows to give a human-readable name for the file. So that's what you can see under the text column. So all of these files here have a user interface section. OK, so now that we've seen all this, let's go back to RWEvrything binary. So what this tool will do first is that it will parse all of the firmware volumes that are in the BIOS region. And it will look for 4 specific files. We'll look for Ip4Dxe, NTFS.exe, SPI Flash, and the DXE Core. The reason why it looks for these specific files, well, for Ip4Dxe and the DXE Core, these are used to find the firmware volumes where to install the rootkit. Usually, the DXE drivers are all in the same volume, so when the tool will find Ip4Dxe, it knows that it is currently parsing the DXE driver's volume, and it will keep it as a candidate for the UEFI rootkit installation. And then the DXE Core can be in another volume. So it will do the same thing when it finds the DXE Core volume. It will keep some information about it. And it will use this volume as a candidate for the UEFI rootkit installation. And the chosen volume will be the one with sufficient memory available on it. And then for NTFS.exe, NTFS.exe is the American Megatron Incorporated NTFS driver. And if it finds it, it will just remove it. And we'll see a little bit more in detail why it does so later on in this talk. And it also looks for SPI Flash. It keeps some metadata about it, but doesn't use it anywhere in the code. Interestingly, SPI Flash is a non-vulnerable DXE driver. So what we believe is that Sednit's operator might have been fiddling with some kind of exploit for this vulnerable DXE driver in order to be able to bypass write protection to the BIOS region of the SPI Flash memory. We'll see that a little bit more in details later on in this talk too. OK, so the next thing it will do is that it will add the rootkit to the UEFI firmware. And the first thing it will do is that it will create a firmware file system file header, which is of type EFI FFS file header. Then it will append the rootkit file, which is a compressed section. And this section will contain two sections. One of these sections is the UEFI executable, so the rootkit itself. And the other section is the user interface sections, giving a name for this rootkit. So the rootkit is called autochk.exe. And then it will write this blob of data at the end of either the DXE driver's volume or the DXE Core volume, depending on where there's enough space. OK, so now that the UEFI firmware contains the UEFI rootkit, the next step is to write it back to the SPI Flash Memory. Once again, before we dig into the subject and what the tool does exactly, I just want to introduce a few things here. So I want to talk about BIOS write protection mechanisms. So the platform, read here, the chipset, exposes write protection mechanisms, and these mechanisms need to be properly configured by the firmware. Today we'll only cover relevant protections to our research. For instance, we won't talk about protected range registers, which is a mechanism to protect some specific areas in the SPI Flash Memory, just because the tool doesn't check for these settings. The mechanism we'll talk about today are exposed via the BIOS control register. So if you want to write to the SPI Flash Memory, you need to set the BIOS write enable field in the bias control register to 1. And when it is set to 1, then you're able to write to the bias region of the SPI Flash Memory. Of course, you don't want any kernel driver to be able to corrupt the content of the SPI Flash Memory. So Intel came up with a protection mechanism. So there's another field in the bias control register called bias lock enable. So when it is activated, what it does is that it will lock the bias write enable field to 0. And here what we see is that this field is readable and write lock once. And write lock once means that once the firmware set this bit to 1, there's no other way to set anything back to 0 than performing a full platform reset. But there's a problem here. The implementation of bias lock enable is actually vulnerable. So how it works is that if bias lock enable is set to 1, and then you write to the bias write enable field, you set it to 1, the value in the bias control register will actually change for a small amount of time, and then an SMI will be triggered by the platform, and the SMI handler will set bias write enable to 0. And let's note here that the firmware needs to implement this specific SMI handler for this mechanism to be useful. But that's not the biggest problem here. Maybe you've guessed it, but what happens if we write to the SPI Flash Memory before the SMI handler sets bias write enable to 0? So there's a race condition vulnerability here. There's a paper about it, and it's called Speed Racer. So how it works, if you want to exploit this vulnerability, what you need to do is that you need to start a thread that will continuously set bias write enable to 1, while another thread is trying to write to the SPI Flash memory. And according to the Speed Racer's paper, it works on multi-core processors and single-core processors with hyperthreading enabled. So Intel came up with a patch for this issue, and it was introduced in the Platform Controller Hub families of Intel chipset around 2008. So what they did is that they added a field in the bias control register. So this field is called SMM bias write protect disable. So it's a bit misleading because of the disable, but you can just get rid of the disable, and then that's what it does. So how it works is that if it is enabled, there will be no way to write to the bias region of the SPI Flash unless all of the cores are running in system management mode. And once again, the firmware must set this bit to 1 in order for this mechanism to be activated. So now that we've seen all this, let's go back to RWEvrything binary. So of course, if I introduce all of these mechanisms, it means that RWEvrything binary checks for them. So it will check if the platform is properly configured, and it also implements the exploit for the race condition. So here's the writing process decision tree. So the first thing that it will look for is bias write enable set? And if it is, there's nothing that will stop it from writing to the SPI Flash Memory, or at least to the bias region of the SPI Flash Memory, so it will write the UEFI image. If it is not set, it will check, is bias lock enable set? And if it is not, well, it will just flip the bias write enable bit to 1, and then it will write the UEFI image. But if it is not, if it is set, then it will check, is SMM bias write protection enabled? And if it is not, well, it will go to race, so it will exploit the race condition. But if it is activated, then it will just fail. So we spoke about SMI Flash, the vulnerable DXE driver, a bit earlier. And what we believe is that they check for it because maybe in another version they are trying to exploit this vulnerability to be able to write to the SPI Flash Memory, even if all of these mechanisms are properly configured. So as you can see from this decision tree, the tool will only work if the platform is misconfigured. So if the firmware vendors would have done their job correctly, the tool would have failed at writing to the SPI Flash Memory, and it would have required way more resources from the attackers to be able to write to the SPI Flash Memory. So this is kind of a great example of how important firmware security is and how firmware vendors could have saved the day, but didn't in this case. OK, so now let's look at what is the sequence of operation that you need to do if you want to write to the SPI Flash Memory. Once again, it's kind of standard way of doing this. I believe it's the only way of doing this, at least on the on Intel platforms. So the first thing you need to find is, as Jean mentioned, the hardware sequencing flash control register. And this register is memory map in the root complex register block. So the first thing that you need to do, you need to write the number of bytes that you want to write to the SPI Flash Memory in the flash data byte count field of the hardware sequencing flash control. Then the next thing that you need to do is you need to set the flash cycle to 1-0 binary, meaning that the kind of cycle you want to do is a write cycle. Then you need to write to the flash address where you want to write in the SPI Flash memory. And you just put the data you want to write in the flash data registers. And then you need to tell to the SPI Flash controller that you want to start the cycle that you just configured. So you do that by setting the flash cycle go field to 1. And then the SPI Flash controller will set one field in the hardware sequencing flash status to 1. And this field is SPI cycle in progress, meaning that the cycle is ongoing, of course. And once it is completed, it will set it back to 0. And it means, yeah, it has completed. So then if you want to write all the data that you have to write, you just loop from step 3 to step 6 until you're done. So let's take a minute and take a step back here. So what we're looking at is a tool that is able to install a UEFI rootkit and write it back to the SPI Flash Memory remotely by software means and like post-exploitation. That's kind of very convenient. What we knew about before was the hacking team's UEFI rootkit, and it needed physical access to be able to deploy it on a victim's machine. So that's really more convenient, as I mentioned. So yeah, and let's just mention here that there are no proof of hacking team's rootkit being used in an actual cyber attack. It has never been found on a victim's machine. We only have the source code and a compiled firmware and some email exchange, but we've never found it really deployed on a machine. So what we did there is that we extracted the UEFI rootkit from the tool, and then we looked at ESET's UEFI scanner telemetry. And turns out we found the rootkit in the SPI Flash Memory of a system, making it the first publicly known UEFI rootkit to use in a cyber attack. So if we go back to the statement that Jean showed earlier in the presentation, that we have yet to observe real-world UEFI malware, well, it turns out that now it's checked. OK, so let's go back to the technical part of this presentation and explain how does the UEFI rootkit work. So the UEFI rootkit is a DXE driver that is called autochk.exe, as I mentioned earlier. And it is loaded by the DXE dispatcher every time that the system will boot. It is unsigned, so secure boot would catch it, given that it is properly implemented. And if you don't know about secure boot, it's a mechanism that will ensure that everything that is loaded by the firmware is properly signed. And I just put the file GUID there just for future reference. So here we have the UEFI rootkit workflow. So a UEFI firmware, when it boots, it will go through multiple phases. The first phase is the security phase, which is basically the root of trust of your system, and then it can check that everything is properly signed. And then on the next phase, the pre-UEFI, well, the next phase, the processor is initialized, the chipset is initialized, and so on. And then we go to the part that is interesting for us, the DXE dispatcher. So that's where the dispatcher is run. The dispatcher will run all of the DXE drivers it can find, and one of these drivers will be the UEFI rootkit. When it's loaded, the UEFI rootkit will create an event. This event will be attached to the EFI event group ready to boot. This event group is signaled by the boot manager, which runs on the next phase of the boot sequence. And there's a notify function, which is basically a callback that is attached to this event, and this callback will contain the actual malicious code. So when the boot manager loads, at some point it will signal the EFI event group, ready to boot event group, and the notify function will be called. The notify function does three things. The first thing it will do is that it will install an NTFS driver. Then it will drop autoche.exe and rpcnet.p.exe. And finally, it will patch a value in the Windows registry. So the NTFS driver. The NTFS driver is needed to get file-based access to Windows partition. UEFI firmware don't really need to have an NTFS driver, since the only thing it really needs to be able to do is to read the EFI system partition where the operating system loader is located. So, well, it's common to have UEFI firmware that doesn't have NTFS driver on it. And sometimes when you find NTFS driver, they don't implement the whole NTFS driver, meaning that they only implement a subset of the functionality that you're expecting from an NTFS driver. And that's why it looks for the NTFS.exe that we've seen earlier that it removes. It's because this specific driver only implements reading operations to the NTFS partition, which is not interesting for the rootkit because it wants to drop files to disk. And Sednit's operator did not come with their own NTFS driver. What they did is that they just took the NTFS driver from Hacking Team's leak. So this NTFS driver was part of the Vector ADK project, which leaked which was part of the leak. And in this project, there was RKLoader, which was the UEFI rootkit, and there was an NTFS driver because Hacking Team's UEFI rootkit needed to drop files, right? So that's what they used. They just built their own version of it, and they embedded it in their UEFI rootkit. Then the next step is that it will drop two files. So that's the code responsible for it. So here you can see that it drops rpcnet.p.exe. And then it will drop autoche.exe. And the last thing that it will do is that it will patch the Windows registry. So to do that, what it will do is that it will open the backing file for the HKLM system hive. And then, because it doesn't have the logic to parse the registry key structures, so what it does is that it looks for a specific text pattern, which is autocheck star. And if it finds it, it changed the last K to E. And it happens to be the registry key that Jean spoke about earlier, so boot execute. So what will happen is that when the operating system will load, at some point, it will run autoche.exe. And autoche.exe, what will do is nasty things. But what's interesting here is that it will revert back the modification to the Windows registry. So autoche will become autocheck again. So if I'm a user logged in Windows, for instance, and I look at my at regedit, I won't see that this modification happened. And the last thing I want to talk about today is how could such an attack have been prevented, and I want to talk about remediation too. So prevention. Well, the perfect mechanism to block this kind of attack is secure boot. So it should really be activated on your platform, and hopefully it is properly implemented. And then you should really keep your UEFI firmware up to date. Just to make sure that all of the latest patches available are on your machine. So it's really a good idea to visit your motherboard website just to make sure that you have the latest version installed. Also, make sure that you have modern chipsets, so something so that you have a platform controller, hub families of Intel chipset, just to make sure that the protection against speed eraser is available. Otherwise, it's kind of there's no way to protect against this this kind of attack. And finally, you kind of need to hope that your firmware is configured your firmware configured the security mechanisms properly, there's not much you can do, but having your platform your firmware up to date. But there's a good news here, is that there's an open source project called ChipSec that allows to perform firmware security assessments. So it will check for all of the bias region protection mechanism that we spoke about today, and even more stuff. So if you want to know if your firmware does the job correctly, it's really the way to go. And finally, remediation. Well, if you have a UEFI rootkit in your SPI Flash memory, the only way of getting rid of it is to reflash your UEFI firmware. It's possible that if you install a UEFI firmware update, if it rewrites the whole bias region section, then you'll get rid of this specific UEFI rootkit. But UEFI rootkit can be in another place in the SPI Flash memory, so if it only rewrites the bias region, it's not enough. But some other updates will rewrite the whole SPI Flash memory content. So yeah, it could work, but it's not a perfect way of doing that. And yeah, if reflashing your UEFI firmware is not an option for you, well, there's not much you can do. You can just get rid of your motherboard or your laptop and just get another one, unless you don't really care having a UEFI rootkit in your system. Okay, now a quick conclusion. So our research proves that UEFI rootkits are not only toys for researchers to play with, but they are a real-world threat used in cyber attacks. So maybe that's something you should keep in mind when you're defining your threat model. And we won't stress this enough. Firmware must be built with security in mind from bottom up. Nowadays, there's a lot of researchers looking into it. So things are getting better, but there's still work to do. So that's pretty much it for us. The white paper for this research is available on at welivesecurity.com. So if you want more detail, you should just grab a copy there. Otherwise, thank you for having us. And if there's time for questions, feel free to ask them. Yeah.
Thanks for presenting the research, very interesting. The question is, if you guys never found, I mean, you were very smart in hunting and finding all these tool set, but if you never found the RWEverything and DXE and all this tool set, how would it be possible to detect such UEFI thing when they're installed? I mean, do you guys have UEFI capabilities or any avenue for detecting things when they are installed without detecting their tool sets?
Yeah, all right. Thank you for your question. So we do have this UEFI scanner that Frédéric referred to. So it's able to scan the UEFI, the SPI Flash Memory. Of course, as you said, since we had access to this UEFI module, because it was embedded into this tool, it was easy to write detection for it and then find it in a real-world system. So you're right that if we don't have access to this tool, it's harder, but we still have the capability to scan this SPI Flash memory and be able to find nefarious things that might be lying around in your SPI Flash memory. Thank you.
Hello. Hey guys, thanks for the presentation. Just wanted to know how, you know, if you're flashing your drive, or if you're flashing your BIOS, but not getting rid of the persistence on the machine, how persistent is that? Does it keep writing back? You know, if you're not finding it, you know, in the on the hard drive.
Yeah, that's a great question. So, of course, as we've seen, this Lojax malware has all these components going from the UEFI rootkit all the way to these userland agents. So, if you're cleaning only your UEFI firmware and that you're not reinstalling your OS, then what happens is that and you're not cleaning this particular malware, then it means that it has the capability to connect to the server and then download something and execute it. So, it does not protect you just reflashing the firmware. So, you really have to clean the old system. You cannot just go and remove the UEFI rootkit, which brings us back to what Frédéric was saying. Like, it's not perfect. Like, the remediation is kind of hard, right? Because you don't know how the rootkit got there, and even by carefully removing everything, it's like you've been kind of own to the deepest level, right? So it's not something that you can get out of easily. I hope it answers your question. Something else?
Hi. Quick question. You said that they were dumping the contents of the UEFI memory and like looking at that before they were writing their bootkit. Was that correct, or did I misunderstand that?
Yep. So the tools we found, so both the dumper and the writer tool, we found them on the same system.
Yep.
And we believe, so of course we have no proof of that, but we believe that they actually dumped the firmware image and looked at it, and then to being able to modify it, and then they used this other tool that Frédéric described to try to write it back to the SPI Flash Memory.
So that led to my actual question, which was like, I guess you then, since you're not quite sure if they actually exfiltrated that dump, then you're not sure like how long it took them to develop any of that.
Oh, okay. No, we don't really know. Sorry.
So if we're operating on the assumption that an attacker is already able to place a driver into DXE that'll be executed prior to ready to boot, it seems to me that a far scarier thing they could do is inject and add handlers into SMM. Is there any evidence that this was happening on those systems as well?
We have no evidence of that, no.
No.
Nice presentation. I wanted just to ask a quick question. The autochk.exe is not digital signed, the version of like dropped by the malware.
No, it's not digitally signed.
And it runs in the same, even if it's not digital signed?
So we have evidence that it ran on several systems. Now, how exactly they were able to do it, we don't really know, but the fact is that in the system that we've seen, we have evidence that this tool was ran in the early stages of Windows. So of course they were able to do it, but as Frédéric said, the system, like the tools they used to actually override the SPI Flash Memory were either misconfigured or old systems, so we might be looking at an attack. They were able to focus on a very old version of Windows they were able to actually own that way. So of course all the newer protection systems might not have been available on the system that was owned by the tool we were discussing.
That's clear. Thank you very much.
Pleasure.
Good morning and thank you. That was a fantastic presentation. Are only Windows-based OSs affected because the APT malware drops the modified autoche.exe?
Yeah, totally. It's Windows only. And the small agent that we found, all the versions were all for Windows, and it's really a Windows-only malware. Or at least the versions we found.
Yeah.
Anything else?
All right. Thank you guys for a great presentation.
Thank you.
Thanks.